Section 6-2 is on the antiderivative of the reciprocal function and another form of the fundamental theorem of calculus. And we're going to take a look at the antiderivative of that reciprocal function here in just a minute. The objective, though, was to find out how to differentiate a function defined as a definite integral with a variable for the upper limit. You've worked with that a little bit. In fact, we defined the ln of x function as the definite integral from 1 to x of 1 over t dt. So we defined one of those functions and looked at its derivative, and you saw several other functions that were defined as definite integrals and then found their derivative. All right. Let's take a look at one property we've talked about here a little bit, but we need to look at it a little bit more closely. We've stated now several times, in fact, all the way back to chapter 3 is probably when we first started stating this, that any time that you know a derivative, at the same time that you know an antiderivative. That if you start out with some function, you go through finding the derivative. If you just reverse that process, start out with the derivative and work your way backwards to get the original function f, you've gone through and found an antiderivative. Anytime you know a derivative, you know an antiderivative. Now, that's true, of course, and we've seen that over and over again. But we've left out a little piece of information here that we need to be a little bit careful with, and we're going to see why that is here in this section. And in particular, it's with this new function we've defined called the ln of x. Here's the property. If f prime of x is the derivative of some function f of x, then the antiderivative of f prime of x is equal to f of x plus c. And I guess I'm kind of using that notation there a little bit loosely here. It's not really f of x because I don't know the constant of the original function, so that's what the plus c is in there for. But you get the basic idea there, that once I know the derivative of a function, f prime of x, I can then work my way backwards from that and find the antiderivative to get back to function f of x. Is basically what that's trying to say. And that's true. We've seen that used over and over again. The one piece of information we haven't added on here is this last line. It says that's only true for the values of x in the domain of function f. So as long as your function and your derivative have the same domain, no problem. You can use this property over and over again like we've done. It's the functions where the derivative and the original function have different domains that we run into problems. Okay, and in particular, we're going to see that with this ln of x function. Let's take a look at an example just to kind of illustrate what this property is stating and what we've actually used over and over again. Let's just say that we've got some function f of x. We can find f prime of x, of course. Derivative of sine is the cosine of x. And so, again, if I find a derivative, I can just reverse this process and find the antiderivative to get back to the original function. In other words, the antiderivative of the cosine of x dx turns out to be the sine of x plus c. Okay? So when we go in one direction here, we end up with a derivative. If we go in the other direction, we end up with the antiderivative. So if we start with this and work our way backwards, we got ourselves an antiderivative. That's basically what we're seeing there. Okay? And of course, these two functions have the same domain, so we haven't had to worry about that extra piece of information that we put in that property up above. All right, so let's see how that relates here then, in particular to our ln of x function. And in particular, we want to integrate, like we said, or find the antiderivative of this reciprocal function, 1 over x dx. In fact, let me remind you here of what we said the derivative of this was. We said that the derivative of ln of x, just using that definition that we had written down, is that definite integral from 1 to x of 1 over t dt, and then using the second form of the fundamental theorem of calculus, we came up with that this was equal to 1 over x. So with that, we should be able to say, well, the antiderivative of 1 over x then is just natural log of x. But you'll notice that there's a little extra piece here, this absolute value. All right, and we're going to see why that's the case, why we need that absolute value in just a second. But it comes down to the fact that the domain of these two functions are different. The domain of natural log, of course, is only defined for positive values of x. We define that function ln of x for values of x greater than 0. But 1 over x, the reciprocal function, is defined for all x except for 0. So that's where our issue is coming in, and why we don't end up with just natural log here. Okay, it's the natural log of the absolute value. Do not forget that. It's got to be put into the problem. It's got to have the absolute value function. All right, so let's see if we can actually show why that's the case here. In fact, we're going to split this up into two cases here, but let me remind you first of all, I guess, of what the definition of ln of x is. So let's just recall here. Ln of x was equal to the definite integral from 1 to x of 1 over t dt. That's how we defined what that was equal to. And that was for x greater than equal, or excuse me, for x greater than 0. Okay? And so therefore, from the second form of the fundamental theorem of calculus, that derivative of an integral form, we were able to conclude that the derivative then of this, this ln of x function, that it was equal to our second form of the fundamental theorem of calculus, says take this function 1 over t and substitute in the upper bound, so it's 1 over x. And then multiply by the derivative of the upper bound, which of course is 1 there. So that's what we learned in the first half. So we're going to use that here to help us prove this, but we're actually going to have to break this up into two cases here. So let's call this case 1. And we'll deal with the positive domain first of all, because that's the easier one of the two, because we can basically use the properties we've just written down to help us out here. Let's take on the case where x is greater than 0. If x is greater than 0, then basically everything that we've just said applies here. In fact, I probably should add on to the end of this that the derivative of ln of x is equal to 1 over x for x greater than 0, because that's the domain of my original function. So in that case, that means that the derivative of ln of x is equal to 1 over x for x greater than 0. And if I know that's the case, I can state that the definite or indefinite integral or antiderivative of 1 over x dx is equal to the ln of x plus c for x greater than 0. Okay, working on the same domain. That's what we said there, that extra piece of that property we were just looking at on the previous slide. You have to have the same domain that you're working with. So that's the easy case. If x is greater than 0, just from the definition in our second form of the fundamental theorem, we know this is true. I guess we're just restating what we just wrote down a second ago, but there we go. Look at case 2. Case 2 is where x is less than 0, and we're just going to really use just a substitution here to help us show this, as well as the first case here will help us go through these steps to prove this. So if x is less than 0, let's define a new variable here. Let's let x be equal to the opposite of u. X is the opposite of u. So that means since x is less than 0 and x is equal to u, that means the opposite of u is less than 0. And if the opposite of u is less than 0, that means u must be greater than 0. If I just multiply through by a -1 or divide through by a -1, don't forget you switch the inequality when you do that. If the opposite of u is less than 0, that means u must be greater than 0. All right. And we can also state if x is equal to the opposite of u, I can find out what the differential of x is equal to. Dx would equal the derivative of a negative u would be a -1 times the differential of u, du, or that's just the opposite of du. All right. So with that information, I can do a substitution into my original problem here. I'm trying to find out what the integral from 1 over x dx is equal to. Let's just substitute in for u, substitute the x's, or replace the x's with u's. So we end up with the integral from, or the indefinite integral of 1 over, instead of x, it's going to be the opposite of u if I substitute that in. Instead of dx, I'll replace that with a negative du. Now notice the two negatives here are going to end up canceling each other out, negative divided by the negative there. So this just turns out to be the integral of 1 over u du. Don't forget we've said here that u is greater than 0. So we want to find the the indefinite integral of 1 over u du where u is greater than 0. Well, we just set up here in case 1 that the integral of 1 over a variable times the differential of that variable, we called it x in this case, is the natural log of that variable plus c when for x greater than 0. So here, all we have is just a different variable. It's u instead of x. So we can find the antiderivative of this. The 1 over u du must equal the natural log of our variable u plus c. And that's for u greater than 0. And now let's do a substitution here of our variables. I can replace the natural log of u with the natural log of u is equal to the opposite of x. We actually said that x was equal to the opposite of u up above here, but of course solving that for u would give us u equals the opposite of x plus c. And that would be for the opposite of x greater than 0, or that means that x is less than 0. So it turns out for x less than 0, our integral turns out to be the natural log of the opposite of x. So let's combine these two cases here. What we just went through and found, we can say therefore, the integral of 1 over x dx, our reciprocal function, is equal to, it's a piecewise function because I have two different domains that I'm working on here. Turns out in case 1, when x was greater than 0, we get the natural log of x plus c. Natural log of x plus c, and that's if x is greater than 0. Case 2, what we just found out was it's equal to the natural log of the opposite of x plus c, and that's if x is less than 0. I think I said natural log. I'm trying to stick to ln of x and ln of the opposite of x there. We have not quite gotten to the point where we've proven this is the natural log function. And so it turns out in either case you're taking the ln of x, in the first case when x is greater than 0, or the ln of the opposite of x. Well, the opposite of x, since x is less than 0 in that case, turns out to be a positive value. It turns out you're taking the ln of a positive number. It would be nice if I could somehow combine that into a single quantity, and oh yeah, that's what our that's what our absolute value function is. The ln of the absolute value of x plus c is equivalent to that. So in fact, the integral of our reciprocal function is not just the ln of x, but rather it's the ln of the absolute value of x plus c. All right. There is the proof of that. Let's actually use this now in a couple of examples. So example 5 says to integrate the secant squared of 5x over the tangent of 5x dx. All right. I'm going to use a u substitution on this thing. And it might not be quite as obvious initially what the u substitution might be here, but I got to keep in mind that I've now learned this antiderivative of my reciprocal function where the variable, or if you will, the inside function is the denominator. 1 over x, the variable there is the denominator. So I'm going to use the denominator of this, which is technically my inside function of my reciprocal function there, as my choice for u. So we're going to say that u is equal to the tangent of 5x. And of course, when I do this, I'm keeping in mind that I have to take the derivative of that, and I need the derivative to be part of this problem. I don't have to worry about the constants, but the other functions that need to be part of that derivative need to show up here. And so as I do this, I'm thinking, okay, tangent is in the denominator, and I see secant squared in the numerator, and oh, the derivative of tangent is secant squared. That's exactly what I needed. So it's secant squared of x times the derivative of secant squared of 5x times the derivative of 5x is 5 times my differential of x dx. I have secant squared of x dx, so I don't want the 5 there. So again, constants are okay to move to the other side. I'm going to move the 5 over there. So we get secant squared of 5x dx. And now I've got my substitution. So let's come over here and substitute in. So secant squared of secant squared of 5x dx. I'm going to think of that as all being in the numerator. You could slide the dx into the numerator there if you wanted to write it that way. And that's equal to 1/5 du. So that's the numerator here, 1/5 du. And the tangent of 5x in the denominator, that's equal to u. Now if you want to, you can bring the 1/5 out front. I'm going to go ahead and do that. Remember your property there for the indefinite integral of a constant times a function there. The constant come out front of du over u. And you should get comfortable seeing this actually in a couple different forms here. I'll write it another way here that the way we wrote this property on the previous slide. I'll write it this way, that I can write it as 1/5 the integral of 1 over u du. That's how we just saw it, 1 over x dx. Or you might even see it written this way, 1/5 the integral of u to the -1 du. All right, you should get comfortable seeing that written any one of those three ways and recognize that's the ln of x, or ln of u in this case, function. That's my ln function. All right, so it turns out that this is equal to 1/5 the ln of the absolute value of u plus c. Don't forget your absolute value. Again, the rule for the antiderivative of 1 over u du is the ln of the absolute value of u. That's what we've done there. And now just replace u with what it's equal to. U we said was tangent of 5x. So we get 1/5 1/5 ln of the absolute value of tangent of 5x dx. All right. Let's take a look at another example here. Example 6 gives us a definite integral this time. So they ask us to find the definite integral from -4 to -5 of x squared dx over 1 plus x cubed. And again, we just learned this reciprocal function, so you should be kind of thinking about that as you see these. The fact that it's in a quotient form, that might help you see that. I'm going to use a u substitution again. And when with using the fact that we know the antiderivative of a reciprocal function, now we look at the denominator as being the choice for u. That's technically still the inside function of that reciprocal function. So we have u is equal to 1 plus x cubed. So du is equal to, the derivative of that is going to be 3x squared times our differential of x. And you can see in my numerator I have an x squared dx. I just don't want the 3, so I'll move him to the other side. 1/3 du equals x squared dx. And now we're all set for our substitution. So we have the integral, and I'll worry about the endpoints in just a second. Remember what happens here when we do a variable substitution with our endpoints. We'll come back and take care of those in a second. And the numerator here is x squared dx, so that's equal to the 1/3 du. And the denominator, 1 plus x squared, we said was equal to u. Now again, remember the endpoints there change, that I can take these values here and plug them into this little formula. This formula tells me how I convert x's over to u values. So when I take let's start with the -4, the lower bound. When I take a -4 and plug it in there, -4 cubed, 4 times 4 is 16 times 4 is 64, and it's negative. So it's 1 plus a -64. 1 minus 64 is a -63 is the lower bound. And now do the same thing for the upper bound. 5 cubed, or -5 cubed, is going to be a -125. 1 plus a -125 is a -124. Don't forget, you change those endpoints. All right, again, if you want to factor out the 1/3, we can bring that out front and write it as a -3, or -1/3 from -63 to a -124 of du over u. I'll go ahead and write this out again several ways. You should recognize it in any one of these three forms here. That's the same as 1/3, the definite integral from -63 to -124 of 1 over u du. This is probably the one that you are going to feel most comfortable with, but you should recognize any one of these. Or again, you can write it as 1/3 the integral from -63 to -124 of u to the -1 du. Okay, be able to work with any one of those. All right, so let's go ahead and evaluate that. Again, anytime you see the definite integral of du over u, 1 over u du, or u to the -1 du, that's the ln function. So it's the ln of the absolute value of u. And remember, with a definite integral, we don't have to worry about writing down the plus c because it's going to end up canceling out anyways. Just indicate your lower bound and your upper bound, and we'll plug those in and take the difference. All right. And this is the reason why we did a change. Well, we needed to do the change of our upper and lower bound here into terms of u, but I don't have to change this back to x's now. I just plug in my new u values for the endpoint. So it's 1/3 the natural log, or excuse me, 1/3 the ln of the absolute value of my upper bound in -124, and then minus 1/3 the ln of the absolute value of a -63, my lower bound. Oops, that's an absolute value sign. And we can simplify that because I know what the absolute value of a -124 is. It's a positive 124. So we can get rid of the absolute value. Drop the minus sign when you do that. Minus 1/3 the ln of, oops, I can drop the absolute value here again, of course. It's just 63. All right. In fact, you could do a little bit more work with this if you wanted to. You could plug that into your calculator and evaluate it and see what you end up with, but I'll just leave it in that form right now. In fact, I guess I'll just take the number they've got in the book there. It's 0.2257 is what it turns out to be if you plug that in your calculator and evaluate it. All right, let's take a look at one last example. And this is the example there on page 276. Example number 8. It says the figure there shows the graph of the function f. And it says let g of x equal the definite integral from 1 to x of f of t dt. So let's go ahead and write that down. Let me make this graph just a little bit bigger here since I'm going to try to plot some points on it. It'll be a little bit easier to work with. So let's say that g of x is equal to, this is part A, the definite integral from 1 to x of f of t dt. And they've given you a sketch of the graph of function f there. That's what they've got sketched for you. All right, so the question is, can you sketch the graph of function g? All right, so the way we're going to do this is we're going to just plug in a few points here, a few x values, and then plot the corresponding x, y values that we come up with for function g. We'll have a series of points and then sketch the curve that goes through those points. We should come up with a pretty accurate sketch of this thing. All right, so let's start out with the easiest one here. And that is starting at the same value of x as my lower bound. My lower bound here for function g is 1. So I'm going to start out with that same value for function g here. Let's start out with x equals 1. So g of 1. If I just replace x with 1 there, I'd have the definite integral from 1 to 1 of f of t dt. Now that means find the area under this curve from 1 to 1. Well, of course, the area under the curve from 1 to 1, there is no area because you're starting and ending at the same point. So g of 1 turns out to be equal to 0. So at x equals 1, y is 0. So let's go ahead and plot that point. Let me put this in red here so it'll be easier to see. That right there we have a value of 0. All right, let's move forward to the next point here at 2. So g of 2 Just replacing the value of x there with 2, we'd integrate from 1 to 2 of f of t dt. Now this means find the area under this curve from 1 to 2. So if you look there, that region that we're talking about is this region right here, which has got, I guess, 2 parts we can think of splitting this into. It's got a square, which I can tell the area of that square. It's 1 by 1, so that area is 1. It's above the x-axis, and we're going from 1 to 2, so the definite integral for that part of it would just be a positive 1. But then you also have this quarter circle, a quarter circle with a radius of 1. I know the area of a circle is pi times the radius squared, and since it's a quarter circle, it's 1/4 that. So pi times 1 squared, that's just pi times a fourth or a quarter of the circle. This is pi over 4. So it turns out that g of 2 is equal to the sum of those two here. That would be 1 plus pi over 4. All right, and pi over 4, if you punch that into your calculator, pi over 4 is approximately 0.7. If you want to get a little more accurate, you can. 0.785, I think, is what you end up with, but 0.7, 0.8 is close enough for us. So I'm going to just say this is approximately, I guess I'll say 1.8. It's actually closer to 1.8. All right, so let's plot a point at x equals 2 that g of 2 is equal to 1.8. So at 2, we'll plot a value of about right here, we'll say. Okay. And we're going to continue with this. So let's move on to 3. So at x equals 3, g of 3 is equal to the integral from 1 to 3 of f of t dt. And again, that means that I've got to find the area from 1 to 3 now. So I've already done the area from 1 to 2. So now if I add on this region from 2 to 3, that's just a triangle. And the area of that triangle is, of course, 1/2. So that means that this turns out to be equal to, oops, do that in the same color that we had up here. This turns out to be 1 plus half is 1.5 plus the pi over 4. And so that's just a half more than what we had above there. So that's going to be about 2.3. Again, that's our approximation, but that'll be close enough for what we're trying to sketch here. So at x equals 3, let's plot a point at 2.3. That's about right there. And you can kind of get the idea of how this is going to keep going here. So let's do the last 2 points that they've got indicated for us here at 4 and at 5. So g of 4 is equal to the integral from 1 to 4 of f of t dt. And so that's equal to, again, let's find the area now from the definite integral, I should say, from 3 to 4. That's going to be this region. Now, because this is below the x-axis, that means that's a negative 1/2. So now we have subtracted off that 1/2 we added on from 2 to 3. So it turns out this is 1 plus pi over 4 again, which is approximately 1.8. So now at x equals 4, we'll plot a point again at 1.8, which is about right there. And one last value here at 5. So g of 5 is equal to the integral from 1 to 5 of f of t dt. And so that's this region right here. It's a trapezoid, so you could find the area by trapezoid. I'm going to see it as a square and a triangle, though. So this is a -1 and -1/2, again, because they're below the x-axis. So again, when you tally these up, you've got a -2 here total that's below the x-axis, and a positive 1.5. So it's going to be a -1/2 plus the pi over 4. -1/2 plus the pi over 4. So again, if you subtract a half from about 0.8 is what we're approximating pi over 4 to be. So that's going to be about 0.3. So again, let's plot that point at x equals 5. We plot a value of about 0.3. We'll say that's about right here. All right. And there's one more point for us to plot here on this sketch. We move forward from x equals 1, but we can, or we should, move backwards as well if we can. And I should be able to find out what g of 0 is equal to. Okay, so g of 0, let me do that over here. G of 0 is going to be the integral from 1 to 0. Remember, you changed the upper bound there. That was x, so we replaced that with the 0. of f of t dt. All right, so let's find out what the integral from, oops, actually one thing I want to change here slightly. You could leave it in this form, but I want to change this actually. Remember, if you swap or change the endpoints there, going from 1 to 0 versus the integral from 0 to 1, it's the opposite result. So it's the opposite of the integral from 0 to 1 of f of t dt. So let's find out what the integral from 0 to 1 is, and then we'll take the opposite of that is what we're going to do. So from 0 to 1, that's this region right here. In fact, that's identical to the region from 1 to 2. So we know this is 1. We know this is pi over 4. So this turns out to be equal to, don't forget your opposite, your negative sign out front there, but the integral from 0 to 1 is 1 plus pi over 4. And we're going to take the opposite of that, so that's approximately, again, 1 plus 0.8 there is 1 plus pi over 4 is 1.8. To the opposite of that's going to be a negative 1.8. So we're going to sketch a point. When x is 0 at a negative 1.8, it's about right here. And so now we've got a series of points. We can kind of come up with a sketch of what this function g must look like. And we can kind of sketch that here. It's got a little bit of a curve to it. That curve can be kind of tricky, I guess, to sketch there, but kind of does something like this. Doing something like that. I missed that point at the maximum there, but you get the idea of what function g of x must look like. And that's how we can sketch that function. It takes a little bit of work to find all those points, but once you do, you get a pretty accurate sketch of what this graph looks like. All right. The second half of this question here, part B, says to let h of x be equal to the integral from 1 to, I'm going to write it as 1/3 x plus 1, or x over 3, however you want to write it, of f of t dt. And the question is, what's h prime of 3? All right, so to find h prime of 3, the first thing we have to do is find out what h prime of x is equal to. And then once we know what h prime of x is equal to, we can then find out what h prime at 3 is equal to. So h prime of x, we've got a function defined as a definite integral where the upper bound is in a variable, a function of x really. So to find the derivative of this, we just use our second form of that fundamental theorem of calculus. The rule says you take this function f of t, and you replace the t with the upper bound, so it's going to be f of 1/3 x plus 1. And then we multiply by the derivative of the upper bound. That's just a linear function. The derivative is 1/3. All right, so there's the rule for the derivative of h. So now to find h prime at 3, we just replace the x in there with 3. So we have f of 1/3 times 3 plus 1 times 1/3. Or that would be 1/3 of 3 is 1 plus 1. That would be f of 2 times 1/3. Yeah, what does f of 2 equal? Well, they gave us a graph of function f up here, so let's go up there and see what f of 2 is equal to. F of 2 is this point right here. F of 2 is equal to 1. So it looks like we end up with 1 times 1/3, or that's just going to be, of course, 1/3. So h prime of 3 is equal to 1/3 there. So even though we didn't sketch what h of x looks like, we could have done something similar to what we did with part A. But even though I don't have a sketch of it, I can still find the derivative of that function at 3. All right, and that is the end of this section here for us.